All right, we're going to do some vsepr structures here. Okay, and vsepr structures just mean that we're going to be looking at how the electrons are pairing up and how that's adjusting our structures. Okay? So every single time you're going to draw the Lewis dot structure first. So same rules, boron and fluorine. Boron can have 3 bonds, fluorine can have 1. So boron goes in the center, fluorine goes on the outside. Okay? And at this point, I know that I have to connect them all with single bonds. I know boron only has 3 valence electrons. I know fluorine has 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so now I just checked. Boron has 3. All the fluorines have 7, so my valences are correct. Now I need to check my octets. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Notice I just count them up in pairs because the unbonded pairs are going to want to stay together, and of course their bonded pairs are going to want to stay together. These ones are bonded pairs because they are sharing. And these are unbonded pairs. I don't call those lone pairs. I tend to just call the ones around the central atom lone pairs so that when you're looking at your chart, your vsepr chart, you don't get confused. Now, the fluorines met the octet rule, but boron didn't. Boron has 2, 4, 6. And that's because boron doesn't have another electron to form another bond. So he's actually happy with just 3 bonds. So this, even though it's not a true octet rule, okay, the structure meets what it needs to meet. Okay, just boron forms incomplete octets. So now I have that. Now I have to code it off of my my vsepr chart. So I have my vsepr chart here. Number of atoms off the central atom. That means how many atoms minus the center. So I have 4 atoms total. I have 3 outer atoms. So I have 3 atoms off the central, okay, because they are bonded off of the central. Okay, and then lone pairs. Lone pairs, I have 0 lone pairs. That means just on the central atom, do you have any extra electrons? I have none. 0 lone pairs. So my code is 3, 0. So I go down here and I find 3, 0. Looks like this, and it's called trigonal planar at 120 degrees. Trigonal planar, 120 degrees. And then in terms of symmetry, this guy, right now he doesn't look symmetric, but if you saw what he looked like in the drawing, oh, I'm still not going to do it justice. Okay, let me see if I can, there we go, that's better. I have boron in the center and the other 3 around. So even though the Lewis structure looks like this, that's not what it's going to be in real life. In real life, it's going to look like this. This is symmetric. If I cut it down any set of directions, I am seeing a similar pattern. So this counts as symmetric. I have no lone pairs, and I have all the same atom on the outside. So this is nonpolar.